For Unit 5, Lesson 1, we'll be discussing thermochemistry. Throughout this unit, we'll be using the term energy. Energy is the ability to do work. We measure energy in joules, capital J, named after James Prescott Joule. Other common units of energy are the calorie. A calorie is equal to 4.18 joules. To know how energy is flowing, we first need to identify our system and surroundings. The system includes the molecules we want to study. For example, a chemical reaction, or in this image, water and ice. The surrounding is everything else, so the beaker, the container, the air. Let's look at an example. Pasta is being cooked on a stove. Which of the following is not part of the system? The pasta, the water, the pot, or the salt? So the system is what we're trying to look at. The surroundings are everything else. So the only thing that would be in the surrounding would be our pot. We have a couple different reactions involving energy. Endergonic reactions absorb energy from the surroundings. And if it is absorbing heat energy, which we label Q, we call those endothermic. So heat moves from the surroundings to the system. The other group of reactions involving energy we call exergonic. Here, energy is being released by our reaction. And when we are releasing heat, Q, we call those exothermic, just like exiting. So heat moves from the system to the surroundings. Let's review our phase changes and determine which ones are endothermic and which ones are exothermic. Freezing, condensation, and deposition all require the release of heat. They would be exothermic. Melting, vaporization, and sublimation all require energy or heat. They would be endothermic. So just like our law of conservation of energy, the first law of thermodynamics states that energy is neither created nor destroyed. It is only transformed. So in other words, the total energy of our universe must be constant. So if the system loses energy, it must be gained by our surroundings. Let's put all this information together in example number 2. When a strong acid is added to a flask containing water, the flask becomes warm to the touch. This is because A, the reaction performed work on the flask, B, the system absorbed the heat from the surroundings, C, the system released heat to the surroundings, or D, the surroundings released heat to the system. Example number 3, when a hot rock is added to a cup of cold water, A, the water and the rock both gain energy, B, the water and the rock both lose energy, C, the rock will gain energy and the water will lose energy, or D, the rock will lose energy and the water will gain energy. Enthalpy is another way we can represent the total heat content of a system, symbolized with the letter delta H. We calculate it by taking the Q, the energy of our system, and usually in kilojoules, divided by the moles of our substance. If we get a negative number out, we know it's an exothermic reaction, and if it is a positive number, an endothermic reaction. We can use enthalpy or delta H of a reaction to convert back and forth between moles and kilojoules. In example number 4, we have the combustion of methane gas, which releases 890.4 kilojoules per mole. That is our enthalpy. We want to calculate how much energy is released with 2 moles being burned. So we need to set up our enthalpy, 890.4 kilojoules per mole, as a conversion factor. So since we are already in moles, we want to put our 1 mole on bottom, and then our value, our kilojoules, on top. And this time it is negative because it's releasing 890 kilojoules, and then simply calculate. Example 5, we have the same reaction. This time we're starting with 22.4 grams of methane instead of moles. So we have 1 extra conversion, grams to moles, and then moles to energy. So how do we measure enthalpy? We use a laboratory technique called calorimetry, and it measures how the heat is flowing in and out of our system, usually to water that is in our calorimeter. To find the Q part of our enthalpy equation, we use the specific heat. Q stands for energy measured in joules, M, mass of our sample in grams, C, the specific heat, which is the amount of energy required to raise the temperature of 1 gram of our substance by 1 degrees, and T is our temperature change, final minus initial. Let's do a couple examples using our specific heat equation. For example number 6, we are trying to find how much heat in joules is required to raise our temperature. We want to take our equation, plug in our numbers, and solve for Q. For example number 7, we are asked to solve for the mass of our sample. Again, use your specific heat equation, plug in your numbers, and solve for M. And that's another AP Chemistry lesson with Miss Gates. Make sure you like this video, follow me on Twitter at Miss Gates Science, and a shout out to my 2018-19 AP Chemistry students.